Let's take a look at the variability of the binomial distribution very quickly, just using some of the standard tools we have available to us in Excel. So I'm going to come over here to the data analysis tool pack. And I'm going to use the random number generator to generate some data. For now, I just use one variable, maybe 10 random numbers, maybe using a binomial distribution. Let's use our 0.15 we see in a lot of our examples to generate 100 trials going through, and let's put our output range right here in column A of our data. So we're just generating 10 quick data points of a binomial distribution to see what we get. So let's now do a descriptive statistics of that and take a look at what we get. Okay, so I'm going to take the same data we just generated. I'm going to take summary statistics and maybe the 95% confidence interval, and I'm going to put the data in my data set right next to the data that we saw. So let's save that data now and see what we get for our statistics. So there's our descriptive statistics of that data set. We know that the mean of the binomial distribution is NP. So I took 100 quick trials at 15% probability of success. So our expected value for this distribution is 15. Out of this sample of 10 data points, we actually got a mean of 15.2. But the confidence interval is fairly wide, plus or minus 2.2 on that. So 13 up to 17.4 could be the real mean of that distribution as we go through. So that's one quick designation. Let's go through and generate a bit more data now. Go back to the random number generator. Okay, so this time let's take maybe 100 data points and put them in obviously a different spot than we did before. Put them over here in column F. So there's our 100 data points. Now let's take a descriptive statistics of that as we go through. We're going to put that data over here in column H, and the data we want to analyze is here in column F. So we can go ahead and do that for the same parameters as before, and there's our data for our 100 data points. Remember our count data set is here. We took 10 and now we're taking 100. For this 100 data points, it actually fell. We have a larger sample, end up getting farther from our expected value of 15. The mean in this data set is 14.66. So clearly there's some variability going on. The higher end gave us much better confidence rather than plus or minus 2.2. We're now plus or minus only 0.8. So we have more confidence in our mean now, but in reality it got a little farther away from what we wanted. So let's take one more data set as we go through. Generate some random data points again. This time let's generate, say, 10,000 data points as we go through. Same basic distribution. Let's put them over here in column K. Okay, so there's our 10,000 data points. Let's take our descriptive statistics now for that. Okay, so now we're going to take our column K data, and let's put our descriptive statistics now over here in M. Let's go ahead and run that. And there's our descriptive statistics. This time we got a lot closer to what we expected. Our expected value for this distribution is 15 across the board. So when we had only 10 data points, our mean was 15.2 plus or minus 2.2. At 100 data points, which should have been more accurate, we got a little farther away at 14.66 plus or minus 0.79. And now with 10,000 data points, we have 14.96. So really pretty close to 15 like we would expect, plus or minus only 0.07. So the larger sample size has helped reduce that level, but giving us more confidence in our mean. But notice how much variability we saw in that mean as we went through. So how do we understand what we should be seeing in that data set? So let's take a basic discrete distribution. We know that it starts at 0, and then we can count 1, 2, 3, 4, 5, 6, 7, 8. Let's go to 10. So if I want to take now my discrete values now, I can take the binomial distribution for that. Binomial dist. Okay, for the number of trials being here in A. We did 100 trials at 0.15. That's what we did on the other side. I'm going to take a false so I can just see the actual probability here, if I can spell false correctly. Okay, so I can take that value now and run that down. So that's now my PDF as I go through. In fact, I might want to insert a header there just so I know that. That's my PDF. I probably want to know the cumulative distribution function as well. So I can take a binomial dist of that with my value here. I did 100 trials at 0.15 and true. So I can build my CDF and my PDF very quickly here as I go through. Okay, now notice my cumulative function at this point is still only up to 10%. That's my warning sign that I really haven't taken this n up to high enough to really understand the data. So I need to copy these two data points down. So what I want to know is that I've covered the entire distribution. So I'm going to extend that down farther. I better plug in my numbers if I expected to actually do the calculation, because that's calculating 0 there. So they're out to 31. I'm still only at 0.999, so I'm going to go back a little farther. Okay. See, once I've got my 1 locked in down here, I know I've covered the entire distribution. If I keep going, it's not truly 1, because as you can see, there's a probability here on the function, but at 10 to the minus 15, the number's so small that I'm not going to worry about it as I go. So I want to know now just, how many successes do I actually expect to get. I can take my expected value of this times my probability. Okay, it will tell me how many of that particular value I will get, which tends to be very, very small as I go through. But if I add these up, you'll notice down here in the corner, the sum of those values is 15. That is the expected value for what I would get as I come through my basic curve. So if I were to take that value and graph it just for a moment, okay, there's my basic curve. So I can see what my curve ought to look like. In theory, the binomial distribution looks like this. I've got an expected value of 15, and I've got plus or minus on that for my distribution as I go through. So that's pretty much what I expect the curve to look like, but that's not quite what we saw here. We did see some variability around that mean based on what I saw. So I know there's a lot of variability that goes on in my sample sizes, and as an engineer, I need to take that into account. So let's generate some more data now just to see how much variability is there really. So this time, let's take a random variable. Let's take a random number generator. So this time let's generate, say, go back to generating 100 data points, but this time let's do 40 variables as we go through it, that kind of distribution with, put the display right here in column A. So I'm going to generate a whole bunch of data now with those kinds of constructs. And what I'd like to do is count how many of each instance I get as I go through that. So I'm going to come here and count that 0, 1, 2, 3, 4, 5, and so on. So I want to get that distribution going here, and I know I want to get down into the 30s. There's 40, so that's far more than I need going through, because I can fill that out. And now I want to simply count the values that I got. So if I so I do a count if for the range of values above it, right? Comma. The value next to it. So I do want to lock that one in. So before I copy it, I've got to make sure I lock in column A on that one. I want to lock in the bottom row 100 there and the top row 100 there. Otherwise I'm going to get very odd results as I copy these through. So I want to take this value, copy it out to the last data set, and then copy it down quite a ways as I go through. So I actually copied more than I needed, so I'm going to get rid of these extra rows here. Okay, so what I've got is if I did it right, I've got my count of the different values going on here. So for instance, in this first sample, I had 8 12s. So then what I can do to kind of illustrate my point is I'm going to take that data and I'm going to graph it by inserting a line graph to see how much variability is there in all of this data. And wow, look at that. Okay, so I've got a lot of variability in my data. This, it's true around the mean, but each sample was a little different, a huge amount of variability, which means when I'm using the binomial distribution in engineering, I've got to be careful. I've got to take that variability into account. If I have a large enough sample, the data does converge around that expected value. But the expected value really only appears with very, very large n. We were pretty close to it when we ran 10,000 trials. But maybe often when I test things or run simulations or I run experiments, I only run 100 or 1,000 trials. So I've really got to be prepared for that level of variability. I want to think of the data as looking like the binomial curve that I expect, but the reality of my sampling is I'm going to get data that looks more like this as I go through. So I've got to manage risk when I'm looking at distributions. If I'm measuring using this kind of distribution, how many defects will I receive? I want to use the upper end of my distribution variability here. So rather than using 15, maybe I should use the 17 or 18 value. So I'm being very pessimistic and I plan for the larger number of defects that I might see. If this is a victory or a good thing, I might want to be more conservative and use the low end of the curve. So I won't always use the expected value of 15 for planning purposes unless I'm confident that my n over time is going to be large enough that my data will normalize around that expected value. So there's going to be a lot of variability in my data, and that's really the key to statistics, is recognizing that variability occurs in all of these distributions, and we need to come to understand that variability.